right. So, almost last talk today. We'll have a surprise commercial break after the last talk. But first, we're going to tell us about reconciling scales in seismology.
Okay, thank you. So for this talk, I'm going to present a bit the work that we've done with a lot of people, actually. And some are in this room, like, for example, Jean-Paul Montagnier, and then Theo Santos also is here. And I will start with actually a geological real Earth problem. And but I promise then I won't show any real data in this talk. Yeah. So here is a cartoon of how we see continents in global seismology. And there are a lot of questions as seismologists that we are trying to answer. And for example, is a classical old problem is what is the nature of this transition between the rigid lithosphere, the continents, and the asthenosphere that is less viscous and that is able to deform. Also, how is the deformation happening? What's the nature of deformation in the asthenosphere? Another question is what are these discontinuities that very often that we see in the continents? And can we also map past deformation in the continents? So if we want to understand and to answer big questions like about the formation of continents or things like that, we need to look at these structures and understand them. And in seismology, to try to answer these questions, what we are looking at are two different things, which are discontinuities and anisotropy. And they are quite useful to look at these things. But the big problem is that we very often look at them completely separately. We use different data sets and we produce different models of discontinuities or models of anisotropy, and very often they are inconsistent and they are very difficult to reconcile. And so, for example, when we look at anisotropy, here is a cartoon. We look at the directional dependence of the velocity of seismic waves. So here we have a seismic wave that travels horizontally. It goes faster than at the same place than a wave that travels vertically. And very often we interpret that as a proxy for deformation in the mantle. So if there is deformation in the mantle shear, all the crystals of olivines, they are going to be in the same direction. They are going to be aligned in the same direction. And at large scales, we are going to produce a large-scale anisotropic signal. So when we see anisotropy in tomographic models, we like to interpret that in terms of deformation, and that's quite useful. But the problem is that a model with discontinuities, completely isotropic, but just discontinuities, can actually produce exactly the same signal. So there is a big ambiguity between small-scale alignment of crystals of olivine and discontinuities. So when we look at anisotropy, we can either interpret it in terms of mantle flow or discontinuities, and those are very different processes, and there is an ambiguity. So if we really want to understand the state of deformation in the mantle, we need to be able to map together at the same time large scales, anisotropy, and small scales discontinuities. Yeah. So a way to look at this trade-off is to look at one. So this will be the only data set I'll be showing. Yeah. So let's look at one position here, one location in the North American craton, one of the oldest continents, and we can look at the vertical and horizontal component of long period seismograms. So those are long period seismograms, and we can extract the phase velocity of surface waves. So those are dispersion curves, and we can interpret them in terms of a 1D model of the Earth. And with the Monte Carlo algorithm, now you all know how they work, we can try to find, and we can find a model here, a simple model with 5 layers, 5 anisotropic layers, and this model fits very well the data. And so we have here 5 layers. Each layer is described by 2 parameters, VSH and VSV. So VSH is the velocity of horizontally traveling or horizontally polarized waves. and VSV, vertically traveling waves. So we have a simple model, 5 layers, 10 elastic parameters, a simple model that fits the data. And of course, this model is not very realistic at all. We know the Earth doesn't look like that at all, but we have a model that fits the data and that explains the data. And the thing is that we can also find a model that is isotropic, that is going to fit the data equally well. And if we do that, if we want to try to find a model that is isotropic, we are going to need to add more parameters. And so here is a model with more parameters, more spatial parameters, 10 layers, 10 isotropic layers. So in each layer now VSV equals VSH, and this model fits equally well the data. Yeah. So again, these two models that are not realistic, but what I'd like to show here is that there is an ambiguity between heterogeneity and anisotropy. And there is a non-uniqueness in the problem. We don't know how to interpret, we don't know, when we interpret the data, we don't know if we should find a model which is isotropic and complex spatially or simple spatially, but anisotropic. And so this is exactly the type of problem that I'd like to use in this, to talk about in this presentation. Yeah. And so usually when we do a global tomography, what we choose is to use and to invert for anisotropy, because when we invert for anisotropy, we are going to need less spatial parameters, and we can get a smooth model and smooth anisotropic models. This is a bit what we are doing when we do global seismology. And so this is an example of a recent full waveform global tomographic model, and it's a smooth model. It's a model obtained with full waveform inversion. So we are actually modeling this is not surface waves anymore. It's the entire wave field, and we are modeling the entire wave field. And it's very expensive because we use numerical methods to do that. And because it's very expensive, we only look at the long periods. We are not inverting the short periods. We are only modeling the long periods. And so we are limited in the frequency band. We have a minimum period that we are looking at. So that means there is a minimum wavelength that we are modeling and that we are able to resolve. We are not able to resolve structure that is smaller, where the scales are smaller than the minimum wavelength in our wave field. So this is why this model is actually smooth and anisotropic. And so we can look at a profile, a 1D profile exactly at the same location here in North America, and this model, this global model, is a smooth model. So if we look at the continent here, so this is the average isotropic velocity, and we're happy because we are in the continent. We see the lithosphere that is old and cold, and so it's a high velocity, and we see a low velocity zone, and so we have a structure that we can understand. But if we look at the radial anisotropy in this model, we see that there is a fair amount of anisotropy, like 5% of anisotropy in this continental lithosphere. And then the question is, how should we interpret this anisotropy? And that's not a simple question, because this could be due to deformation, past deformation, alignment of crystals, or maybe it's just due to small scales that we are not able to resolve, and we don't know that, and that's a problem. So we can make a first-order inference and interpretation with this model, but it's difficult to understand in more detail the processes that are behind. If we want to understand the formation of continents, we need more information. We need to know the small scales. We need to know the discontinuities, and we need to add extra information. So this is not enough. This is an effective model. This is a model that is smooth, that is just an average, but that doesn't represent the true Earth. The true Earth has a small scales, and we are not able to image these small scales, and this is really a problem. We need to add extra information here, maybe from geology, from mineral physics, from geodynamics, to try to make inference about the continents. So to summarize a bit this situation here, let's look at two fields. We are seismologists here on the right. We make models that are smooth, and we are missing the small scales. And on the other side, there are other fields like geodynamics where they are able to model processes and where they see very small scale structure. So we know the Earth might look like this on the left, but we only see a smooth, effective average here on the right. Here we are two fields that are solving very different equations, partial differential equations, but very different equations, and they look at very different things. Here we see a smooth model, which is seismic velocities, whereas on the left it's temperature, composition, and viscosity, and so, for example, here in red is the amount of basalt, and in green is like depleted mantle. So we see very different things, and still it's difficult to reconcile these different fields, these different views of the mantle. Right? And so when we look at them, we can also always like talk to each other between seismologists and geodynamicists, but we can make qualitative inference, but it's difficult to communicate. And so we really would like to be able to map and put small scales into these models. So this is a bit what we are trying to do, and it's quite a difficult problem. We try to ideally to have an algorithm where we do the two at the same time, where we have a tomographic algorithm and a geodynamical algorithm where we have small scales and large scales all together at the same time. Because the Earth is multi-scale, and if we want to understand processes, we need the full range of scales. And so, okay, so this is a very ambitious problem. So, but to tackle that, we decided to use actually a toy problem that is going to be much simpler, which is the marble cake mantle model. And so this is an idea that comes from the 80s, and that's quite old. And the idea is quite simple: is that when subducting slabs are subducting, and they have a different composition than the rest of the mantle, and then they mix in the convective mantle, and you end up with a mantle that looks like a marble cake with two phases, like basalt and depleted mantle, black and white here, and you have a mantle that looks like a marble cake, and the geodynamicists and geochemists they have used this model that looks very simple, but that has a lot of nice properties, and that can be used to describe the mantle. And so we decided, okay, let's try to bake a numerical marble cake. So here this is going to be our toy example. We have just a contour. We are a white anomaly within a black background, and we are following the contour, and we are going to deform the contour in the convecting fluid. And so this is what's happening. So it's quite simple. It's not really a geodynamical model, but we just would like to get a model here with a lot of small scales. Actually, the spectrum of this is a self-similar spectrum. You have large scales and small scales, and there is no typical scale here. And we can build a model like that. It takes some time, numerical time, but we can produce models like that, and we can say, okay, then we know the Earth is going to look like that. This is going to be our geodynamical model in this presentation. Okay, so we have this geodynamical model, and we'd like to see how, the question is, how do we see this model? If this was the real Earth, how, as seismologists, we would see this model. And for that, there is a theory that has been developed recently, and this is our colleague Yann Capdeville that has been working on that for now like over 10 years. And the idea comes from solid mechanics. The idea is to compute an effective medium. If you give a complex medium here, we have a software code to compute an effective medium that is going to be equivalent for long period surface waves. So that means from the wave equation at long periods, these two models are completely equivalent. The wave equation behaves exactly in the same way in these two models. So that means, for example, if you imagine a long period wave field that is propagating through this model here, a complex model, and the wavelength is much larger than all the small scales, the wave field is not going to be sensitive to all the small scales. It's only going to see an effective average, and this is the effective average that we are looking at. And when we compute this effective average, we might think, oh, it's just a smoothing. But it's much more complicated than a smoothing. It's a nonlinear smoothing, because when you do that, you actually produce artificial or extrinsic anisotropy. This is the anisotropy, the long wavelength effective anisotropy that is produced by the small scales. So this is radial anisotropy, it's the ratio between vertically propagating waves and horizontally propagating waves. And you see it's a bit intuitive when you have horizontal layering, you have a lot of horizontal layers, it's going to produce, at long period, it's going to be equivalent to positive radial anisotropy. And when you have a lot of vertical layering here, a lot of small scale layering, you get negative anisotropy. So it's a nonlinear smoothing, but it's very fast to compute this relationship. So for any geological model, we can compute an effective equivalent model. And this is very useful, and there is available software to do that. So if you want to try, if you have any geological model, and you want to see how it would be seen by seismic tomography, you can use that. It's a bit equivalent to the tomographic operator. What we are going to assume here is that we have an approximation of the tomographic operator. So that means we are going to place ourselves in the case where we imagine we have sources and receivers everywhere, and we are able to get the best picture given the frequency band that we have of the field. And if we assume that, then we have an approximation, we have the tomographic operator. So that means for any complex model here, we can compute very quickly what would be seen by tomography. So you can put faults, anything, as complex as you want here on the left, and we can compute what would be the tomographic image, the smooth tomographic image that you would get if you were to do a very good full waveform inversion with a limited frequency band. Yeah. So in this averaging, you see on the left, you have a complex structure that is spatially complex, but the tensor is simple, it's an isotropic tensor. Whereas on the right, we have very simple spatial structure, but the elastic tensor is complex because we add an anisotropy. And so yes, this is the assumption that we're making. The homogenization is the tomographic operator. And now what we want to do is to pose an inverse problem, because now what we observe is the tomography. From a tomographic image that is smooth, that is an effective medium that we cannot interpret, can we go back to the geological structure? We have a forward operator that is numerical and very quick, and we'd like to do the inverse. And so this is an example in a global tomography, but it's a problem that can be quite general. Now, this is an example of exactly the same problem, but for the crust at a very, very smaller scale. Here we are at the scale of 100 meters, and there is a model here with channels and sands, so those are river channels. And so if we were to do like exploration geophysics, we will image this medium like that, like a smooth medium. And the goal will be, again, to go from this smooth tomographic image to try to see where are the river channels. So it's the same problem, it's a downscaling problem, but at a very different scale. And of course, this problem, they are going to be non-unique. We are taking a smooth average, and from the average, what I'm saying is that we'd like to go back to the small scale medium. It's impossible, of course. So what I'm saying here is that we have numbers, we observe the average, and from the average, we want to go back to the numbers, which is impossible, it's non-unique. And so we need extra information to be able to solve the small scale structure. So a way to a bit to summarize the problem that I'd like to talk about. It's a problem. We have seismology, we have large scales. We want to downscale it to find a model here on the left that is going to be small scale. But because we want to small scales, we don't have enough information. So we want to include information from geology or from geodynamics. So this will be a way, if we think about it in terms of a Bayesian formulation, we'll have the data will be the seismic tomographic image, and the prior information will be geology or geodynamics. We want to include prior geological information into our model. Okay, so this is the problem that we are interested in. And I'd like to show two examples of two ways of solving it. So there are still ideas and preliminary results. There are no data or anything. And so those have been the projects of Navid Ejazian and Theo Santos. Theo is here. And the two approaches we've tried, they are from two very different fields. The first one is going to be a multi-point statistical approach, and the second one is a deep learning approach. So let's start with the first one. This is a work of Navid Ejazian, who was a postdoc in Lyon. He's finished now, and the idea is to include a priori information from geology or from geodynamics. The idea was to use multi-point statistics, and so multi-point statistics it's a field with a big community, and that is very active in hydrogeology or in geostatistics. In seismology, we don't use that. In global seismology, we don't use that this type of problems of methods a lot, but they are used a lot to describe the statistics of morphological or subsurface structures. And so the algorithm that we are going to use is an algorithm that was developed by the group of Philippe Renard in Switzerland, and it is going to be the direct sampling algorithm. And this algorithm is quite simple. It's actually an interpolation algorithm. The problem is really a 2D interpolation. We have an image here, and we have pixels that are already reconstructed. We have points, and we just want to interpolate these points. It's an interpolation problem. And so there is a lot of ways to interpolate these points, but what we want is that the interpolated image has a structure that looks like that. And when I say look like, it's going to be difficult to define what does look like mean. But I want this reconstructed image, my interpolated image, to look like a training image, to have the same structure. And so here, for example, we are in hydrogeology, where we have rivers that have a different porosity than the background. And so I want the simulated image to look like this texture is. So I want to use this texture here as a prior information in my interpolation problem. And when this algorithm is run, we have an image where the points have been interpolated, and this image looks like the image on the left here. And so to describe this algorithm, which is called the direct sampling algorithm, Philippe Renard as an example that comes from actually text generation. Is going to do exactly the same thing, but with the text generation. I'd like to show you how it works, because it's nice to understand the algorithm. So this is an example from Philippe Renard, who is in Neuchâtel in Switzerland. Yeah. So the idea is so our training image or our a priori information is going to be a text, which here is going to be a novel by Gustave Flaubert. So this is going to be a French text generation. And it's going to be this is a novel from Gustave Flaubert. And there is a full book, and the full book is going to be our training image. And we want to reconstruct a text, that's the problem, we want to reconstruct a text that looks like the novel. And the very naive way, the zero order reconstruction, the first thing that we can do is to look at the histogram of the book. We look at histogram of letters in the book, and we say, okay, we have a lot of E's, and we don't have a lot of K's because this is French, or we don't have a lot of Y's. And so this is the histogram of the book. And we can try to reproduce a book, we can reproduce a text that follows exactly the same histogram. If we do that, we get a text like that. It doesn't look like anything, but at least if you take the histogram of this, you have the correct histogram. So it's a first approximation, yeah. It's a first reconstruction, it doesn't work at all. But now you can say, okay, instead of having a histogram of letters, I can do a histogram of pairs of letters. Like instead of counting the number of A's and the number of B's, I can count the number of AA's, the number of AB's. So there are not a lot of AA's in French, but you have a 2D histogram. And you can reconstruct a text that follows this 2D histogram. And so this is a simulation at order 1. And you see that, I don't know if you can read, but it doesn't look like anything, but still, yet you see, for example, after a comma, there is a space. Because after a comma, there is always a space. After a period point, there is always a space. So now it kind of starts to look like a text. And of course, we can go further. We can go to order 2, and we can store a histogram, a 3D histogram with all the triplets of letters. How many times I have AAA, or how many times I have AAB. So, we can store that and sample that. And so here you see that we can start to recover some words that are actually French. L, D, grand C, son, I can start to read it. And it doesn't make sense, but I can start to read it. So if we do that, if we keep going like that, of course you understand that we'll have to store a lot of things, and we'll have a memory problem, because we have to store everything. If we want to go to order 5, we have 5-dimensional. So if you have 25 letters, it's 25 to the power of 5. You have to store a lot of things, and it's a problem. So the idea, the trick of this algorithm is very, which is very nice, is to directly sample the text. So this is actually the training text, or the training text, the prior, the book that we're trying to reproduce. And we start with, for example, here 2 letters, P and A. And the question is, after a P and an A, what's the 3rd letter? And instead of having to store everything, we can just go and randomly sample the text until we find an occurrence of P and A. And the 3rd letter will be the letter that we just add after the P and an A. So for example, I'll randomly sample the text until I find a PA. There is 1 here, and after there is an R. So I can add an R, and so on. And so I don't have to store anything. And so with that, I can go to an order, I can go to as high as I want as an order. So now we have PAR. I can sample the text until I find an occurrence of PAR. I take the 4th letter and I add it. So if we do that, for example, we can do that to up to order 13. And so now we actually have something that can be read. And so I read it in French. Les affections et indiquent les pièces de verre qu'il faut imaginer pour se reconnaître. It doesn't mean anything, but it's French. And and we have something that looks like the text. So that's the important part, and I'll come back to that. It doesn't mean anything, so it's not physical, but the texture at order 13, the statistics are kind of correct. And that's the thing that can be discussed after. Okay, so that was an example with a text, and the idea is to do exactly the same with an image. This is a cartoon. I have an image. And so now we are back to the interpolation problem. We have here pixels that have been already reconstructed, and we want to just interpolate these pixels to reconstruct an image. So we are going to randomly choose a pixel. And the goal here is to reconstruct the value of this pixel. So we are going to look for the pixels that are close within a range. So there is a parameter to define, and to build a template. And so those are the 3 pixels that are around the pixels that we want to reconstruct. And now we are going to take this template and look randomly, as we were randomly looking into the text, until we find a match. And of course, here, when I say a match, we have to define a norm and so on. But we are going to randomly sample the image until the template has a good match. Here, the orange is in an orange area, the green pixel is in a green area, and so on. And the pixel to reconstruct is in a blue place. So then it's a blue pixel, and we are going to add blue here. And we add blue here. And then we go to a next pixel, a random pixel, we choose it, and we look for the pixels that are within a circle. And again, we have another template, and we iterate. I am looking into the training image where I have a match between this template and the image. And I am here, I have found a match, and I am in an orange area, so this is going to be an orange pixel, and I reconstruct it here. So with that, I can reconstruct the full image. It's going to be one realization, and I can do it again, and I'll get a second realization, and so on. Okay, so that's the idea. Yes?
If you were to do that very long, I mean, I can see the algorithm failing very soon because there's no match anymore. Does that happen, or is it just...
So sometimes there is no match, and then that's why we need to define the norm. There is never a match, especially if the values are continuous, are real variables. So you actually sample in practice, what we do is we actually sample the image for like a given number of iteration, and we find the place that minimizes the norm, and we put a pixel there, yeah. So there is a lot of choices here, yeah. And so, okay, so this was for an image given by one variable, but we can extend that very easily to a 2 variable. Now we have one variable here, which is, and a second variable, and we are going, it's still an interpolation problem, and I want to reconstruct I want to interpolate these pixels here in these 2 variables. So it's exactly the same thing, but we are in 2D now. So we randomly choose a pixel here to reconstruct. We look at the templates, the pixels that are around. We have two templates, and we're going to randomly sample the image until we find a match. And of course, when we randomly sample the image, the pixels, they stay together, right? Because we want to be at the same place. Okay, so that's an extension to 2 variables. So yeah, we randomly sample the space and so on. So now let's see how this works with a toy example where we have 2 variables. And this is something that we've completely made up here. But here you see, you already can guess that we have tried to make a variable that is going to be small scale and a variable that is going to be large scale. A variable where we have layering and a variable where we have actually the direction of the layers. Actually, here the second variable in the black and white is the angle of the layers. So if you have horizontal layers, you'll have black, and vertical layers, you have white. So it's a kind of a way to try to approach our problem where this is going to be geodynamics, and this is going to be seismology, where we see the anisotropy, the direction of layers. And so we have this as a training image, and we can try to reconstruct an image here like that on the right. And so that's an interpolation problem. Again, we try to reconstruct what's in between the points. And so, okay, so now the idea here was to say, okay, instead of saying that we want to the already reconstructed pixels are a bit everywhere, what we are going to say is that all the pixels of one variable are already reconstructed, and all the pixels of the small scale variable are not reconstructed. But it's still the same algorithm. I'm just saying all the pixels here are already reconstructed and all the pixels here are not reconstructed. And so if we do that, you see that we are going from an interpolation problem towards a downscaling problem, because I'm saying I know completely fully the second variable, the large scale variable, and I want to recover the small scales. You see here that this is going to be the data, and this is going to be our model, and we are actually going to go from the data to the model. So you see, for example, here in the middle we have black, and we want that means we want, when we are black, horizontal layering here. In the corners we have white, that means we want vertical layering. So we know the type of layer, and this tells us what type of layering we want, what's the angle of layering, and this image here tells us the structure of the layering. And so if we run this algorithm like that, here is what we get. So we get an image here, reconstructed image, which is a small scale. So from large scales, we reconstructed the small scales, and the small scales, they have the correct structure. They look like the training image, even though we don't know how to define to look like here. Yeah. So it's a downscaling. So we've kind of solved the downscaling problem. Here we went from the tomography to geodynamics, from large scales to small scales. So now, yes?
It sort of looks like a convolution of the two images. Is that kind of correct mathematically almost?
So the convolution, I guess it's a linear operator. I guess here it will be a non-linear. Yeah, here it's a kind of non-linear. Yeah, or deconvolution, right? Because we want to. Yeah, the convolution will be to go from small scales to large scales, and that we are trying to deconvolve. Maybe it's a way to put it. Yeah. So now let's try to apply that to marble cakes. Our training images, they are going to be like that, marble cakes that we are able to generate. And for each of these marble cakes, we can homogenize them and to compute an effective equivalent, and we can look at the effective equivalent medium. So those are going to be our two variable training images. Now the question is, given a long wavelength image, here is the anisotropy, there is a full tensor actually, can we try to recover the small scales that are behind? If we run this algorithm, here is what we get. We get a marble cake, which is not a geodynamical marble cake, it's kind of a statistical marble cake. So of course, if we show that to a geodynamician, they are not going to like it, because it's not really geodynamics. But still, we are able to recover small-scale structure that look like a marble cake, and we can compare it to the true model. So this was a synthetic example. Here on the left, you have the true model that we homogenized. So we have the tomographic image here. From the tomographic image, we recovered this, and you see that we can recover most of the small-scale structures. Now another example, I'm back to the other example with the channels and sand. Here we have channels, a model with channels. We can homogenize, we can compute the effective equivalent model that we would observe with seismic tomography. We can have generate a lot of models like that with their associated tomographic image. And now the question is, from the tomographic image, can we downscale to recover the small scale structure? And this is what we recover. We recover things, a structure that actually look like rivers, and we can interpret them in terms of river. And if the question is, where is the river, we can actually give an estimate of that. Yeah. And for reference, this was the true model here. So you see some channels that we are able to recover. And this is only one realization. We can run a lot of them. Yeah. Okay, so that was the first part, and now I'd like to talk about the project that Theo is working on, which is a very different way to solve, to address a bit the same problem, which is a deep learning approach. So we are back to the same problem. We have seismology, a tomographic image. We want to downscale it, and we want to add extra information, a priori information, geology and geodynamics. So we have a problem here because we are solving an inverse problem, and we'd like to recover an image that looks like that. And this is a very complicated image. If you look at the spectrum of that, you have a lot of high frequencies. This is an image, I guess it's like 100 by 100 pixels, so it's a lot of pixels. And the question is, how do you parameterize this image? How do you describe or represent this image? If you want to invert for this, you need to parameterize it. And of course, we cannot parameterize it with Voronoi cells. It wouldn't make any sense. How do we parameterize this? And this is really the question that we've been interested in. To parameterize this image, we want to have a function, we want to be able to describe this image with a low number of parameters. Because if we are able to describe this image with 10 parameters, then we will be able to sample this space, a 10-dimensional parameter space. That will be easy. So we want to be able to describe this high-dimensional image with a low dimension in a low-dimensional space. So this is a bit the story of the snake that Klaus was talking about. We want to have a low-dimensional space to represent this high-dimensional image. Yeah. Of course, we could use the geodynamical parameters, the boundary conditions, that we have used to create this geodynamical model. But then this function will be very, very expensive to compute, so we don't want to do that. And to illustrate a bit this problem, let's imagine that we have geological structure that looks like that, where you have like a little faces, and this is our geology. We know that the Earth is made of little faces, and we want to be able to represent or parameterize these little faces here. It's not simple because you have a lot of high frequencies here. But for example, if we define these little faces by their center and their radius, we have here 9 parameters to describe this image. X1, Y1, and R1 is the center, the position of the center, and the radius. So you see that with 9 parameters, we have been able to describe an image like that. So we'd like to do the same thing for a marble cake. And so the idea was to use for that a neural network. And so I'm not going to talk too much about neural networks because I guess tomorrow the full day is going to be about artificial intelligence. I'm sure like Leonard will explain that tomorrow. I'll just say that we are using here a function where the output is going to be able to be computed. We are able to compute the output from the input very quickly, and the function here is differentiable, and that's quite important. Yeah. So we can train a network. This network is defined with weights. We can optimize and train this network so that from a low-dimensional space, for any point that we choose in this low-dimensional space, we are going to produce always a marble cake, or always a figure, an image that looks like a marble cake. So we can train a generator to produce images that look like a marble cake. So here we have a generator from a low-dimensional space. We have an algorithm that produces images, and we want these images to look like marble cakes. And again, I'm not saying anything about when I say looking like. I don't know exactly what I'm talking about. Yeah, I'm just saying, okay, this image doesn't look like marble cake, so we are going to train the algorithm, the network, so to not produce images like that. And then if the algorithm produces an image like that, we'll be happy and we'll optimize the weights so that the generator, the neural network, produces images that look like marble cakes. So then the question is really, how do we tell whether an image that has been produced here looks like a marble cake? And to do that, one possibility is to use another neural network, a discriminator. So here we can train another network to discriminate and to see whether this image looks like a marble cake or not. Like we train a network to discriminate between cats and dogs. We can train a network to say, where you give it an image and it says, oh, it's a cat, it's a dog, it's a cat, it's a dog, and so it's the same thing. So here we are going to have 2 networks, neural networks that are going to compete. They want to do different things, and we train them at the same time. The discriminator wants to discriminate what's a true marble cake and what's not a marble cake, and the generator wants to fool the discriminator because we train the generator such that the image generated by the marble cake is going by the generator is going to be seen as a marble cake by the discriminator. Okay, so these are algorithms, GANs, generative adversarial networks, that have been developed and that are used a lot these last years. And after a while, we start to have an image generated that looks like a marble cake. So this is not a geodynamical model. This is an artificial image that looks like a marble cake. Yeah. And so here is an example. For example, we can train a GAN, a generative adversarial network, to produce images that look like people. We train it with a lot of images, pictures of people, and those are actually pictures that are not pictures that have been produced by a network. And so we can do the same with neural networks, with marble cakes. So here we have a random marble cake generator. Very quickly, and this is when the network has been trained, we can very quickly produce as many marble cakes as we want. And so here the dimension is 30 dimensions. So we are, from any point in this 30-dimensional space, which is not a too big space, to sample with an MCMC, for any point within this space, we can produce an image here like that looks like a marble cake. So we are going to be able to sample the space of marble cakes. And so here is my space of marble cakes. This is my model, and I know that any point here will produce a marble cake, and this is going to be quite useful because now that was a way to include a priori geodynamical information into this into the problem. So I'm only sampling marble cakes. For each point in this space, I can generate a complicated marble cake figure, and I can also very quickly homogenize it. And then I can compare it to a tomographic model, to the data. And so now and by taking the difference between the two, I can compute a likelihood or a posterior value. And then we're back to a problem where we can do MCMC. We can sample a distribution for any point in this 30-dimensional space. I can compute a posterior distribution, and I can sample this space, and I can describe the probability of a marble cake given the observed tomographic image. And yeah, we do MCMC, and we actually are going to produce a lot of different points. And so here is the solution. The solution is not a single point. We are in a Bayesian framework where we are sampling the solution. This is the data. This is a tomographic image with, this is isotropy and this is anisotropy. And the solution to the inverse problem is a multidimensional, a 30-dimensional posterior distribution in what we call this latent space. And that's it. The solution is the distribution. And now, again, we have a problem. How do we describe, do we make inference here with this distribution? And what I'm going to show here is like the most simple, the most naive way, and I'm sure it's not the best. It will be to take all these samples here and to generate marble cakes, because they have an equivalent marble cake. So we have actually 1 million points here, or a lot of points. We have a lot of marble cakes, and we can just average, take the mean in the image space. And this is the mean of in the image space. So this is kind of a way to look at this posterior distribution. And so from the tomographic model, we recovered a model that looks like a geodynamical model. And then when we homogenize it, it fits this data. And so for reference, here was the true model. And so, for example, I think Theo likes to call this structure the trumpet. And you see that we actually recover the trumpet, and we can see that we do recover some structures at small scales from a model that was a large scale. Yeah. Okay, so this is of course very preliminary. It's just a toy examples, but what I've tried to show you is that we are trying to reconcile different fields, seismology and geodynamics, that see the Earth at different scales, and we're trying to put them together. Also, I'd like to say also that we should not directly interpret tomographic models because they are effective images. They are not the true Earth. They are like equivalent Earth. And then in a second time, we can combine this effective Earth that we have obtained from tomography with independent information, higher frequency or geodynamics to infer physical structures. Yeah. And so here, this idea of combining two different fields, it's a bit ambitious. We are really at the beginning. We are going to face a lot of problems, but I guess we should follow the idea of Albert Arantola. We should be ambitious, and we should believe that we can do it. Yeah. Okay, thank you. I'll stop here. Yeah.